Hello class, welcome to this lesson on 8.2. We're going to actually finish up 8.2 in this lesson, part 2, the z-test for a mean. So the essential question for this lesson is, what is the specific statistical process for testing hypotheses involving means for large sample sizes using critical values, as opposed to p-values, what we did in part 1. So remember that the learning goals were the same as was repeated earlier, but now we're focusing on the last four. So performing a z-test like we did before, finding critical values, finding rejection regions, and using rejection regions for the z-test. So we're covering the last half of those goals. So the vocab, again, we're going to be talking about rejection regions and critical value. All right, so let's go ahead and do a quick review of 8.2 part 1. So if you recall, the z-test for a mean can be used when the sample size is large enough or when the population is normally distributed and the sigma is known, the population standard deviation is known. So those are the two criteria that need to be, one of them have to be met for you to be able to use a z-test for a mean. Okay. The other thing that we discussed was performing z-tests with p-values. So the way to perform a z-test with a p-value is to compute this test statistic using the formula z-test is x bar minus mu divided by sigma over square root of n. Once you calculate the test stat, then you need to compute the p-value using the z-table. Again, and that depends whether it's a left-tailed, right-tailed, or two-tailed test. And then you want to compare the p-value to alpha, the level of significance, to determine whether you want to reject or you want to fail to reject. Again, if the p-value is less than or equal to alpha, you reject. If the p-value is greater than alpha, you fail to reject. All right, so now we're going to discuss in this lesson critical values and rejection regions. So what are those? So first off, another way to perform a hypothesis test other than the p-value method is using critical values and rejection regions. So what do those actually look like? So let's give you a quick example. Let's say we had a two-tailed test, right? So clearly we know we have both tails involved, right? Left and right tail. Now what you're going to do is you're going to divide the normal distribution into essentially two regions, okay? A rejection region and a non-rejection region. So in the rejection region, that's where you reject the null hypothesis. The non-rejection, that's where you fail to reject it. Okay, makes sense, the wording. And the divider, the number that is used to divide those two regions from each other is called the critical value. Okay, and we use ZC for that because we're going to be calculating z-scores, and so in order to distinguish a z-test from a critical value, a z-critical, we use ZC for z-crit, z-critical. Okay, so that's what we use for the critical value for the z-test. All right, and that's essentially what you need to know is you need to calculate the critical value so that way you know what's the rejection region versus what's not the rejection region. Okay, and if you're in the rejection region, again, we reject the null hypothesis. And this is how it looks like. All right, so notice that the rejection region is not the same thing as the p-value. Those are two different things. And therefore, that's why on the previous lesson, I shaded the p-value blue. And in this region, and in this lesson, the critical value, I will shade it red. Okay, so again, the rejection region is the range of values that are not probable for the null hypothesis. So basically, if you're in that region, that means it's not probable, and therefore you reject the null hypothesis. So the rejection region, again, we said is not the same thing as the p-value. The critical value separates the two regions, the rejection from the non-rejection. So how do we go about finding the critical values? So if we want to find the critical values, well, first off, it depends what type of test you're dealing with. So if you have a left-tailed test, that means you want to find the z-score when the area equal to alpha. Remember, alpha is your level of significance here, and that's what you choose, right, when you do the test, or it's given to you. So if you know that your alpha is 1%, then you need to find an area of 0.01 on the z-chart, and then whatever z-score relates to that is the z-score that you use for the z-critical. For the right tail test, you're going to take that level of significance and you're going to do 1 minus that. And then you look up that area, and that will tell you your z-critical for the right-tailed test. Now you can imagine that if you have a two-tailed test, you'd have to divide your alpha by 2. That's exactly what you do here. You take your alpha and you cut it in half. So if your alpha was 5%, then when you cut it in half, that's 2.5%. So it's 2.5% on each tail. So that means to find the left side, so over here, if you want to find the left side, your left, my right, in this, in this demo. So if you want to find the left side, you need to look up an area of 2.5% for the example of 5% that we said earlier. And then for an alpha of 5%, you need to, for the right tail, you look up 1 minus 5 divided by 2. All right, so that's how you find the critical values for the different tails. So let's show you that with an example. So find the critical value and rejection region for a right tail test with alpha is 5%, which is what we were talking about earlier. So if I wanted to do 5% and it's a right tail test, then that means I need to do 1 minus alpha, right? So this means 1 minus alpha, and my alpha is 0.05. So if I got to do 1 minus alpha, that's 1 minus 0.05, which means my area is 0.9500. So I need to get as close to 0.9500 as possible. So this means I'm going to look this up on the table. I'm going to look up 0.9500, not the z-score of 0.9500, the area of 0.9500. So I need to get as close to that as possible. So the area that is closest to that is one of those two. Basically, either one of those two will suffice. Okay, so that's you could say that's about 1.6. 1.64. So you could say that the critical value is 1.64, or you could say it's 1.65, because either one of those would be correct, and that's because these are the same distance apart from 0.95. So take your pick. So we're going to choose 1.65, but you can choose 1.64. It's not a big deal. All right. So therefore, my z critical is I think in my diagram I may have chosen 1.64, but so I'm going to write both of them just to be safe. So 1.64 or 1.65. So take your pick, either one. So let's go ahead and show this on the diagram. So we know we have a right-tailed test, so I did choose 1.64 on the diagram. All right, but either one would be sufficient. And that's how my standardized normal distribution looks like. So it cuts off at 1.64, and it's a right-tailed test, so the right side is shaded, and that right side is my rejection region. That left side is my non-rejection region. And notice that the area, that area corresponds to the 0.05 that I found earlier. Okay. My level of significance. So basically, this is my alpha. Okay. All right. So let's do another example. So example 2. So find the critical value in rejection region for a left tail test with alpha 0.01. So since it's a left tail test, my area is equal to alpha. So my area is simply 0.01. So I'm going to look that area up on the Z chart, 0.0100, as close to that as possible. So let's look that up, see where we're at. So if you go to your areas, you want to be on the negative side of the Z chart, not the positive side, because the positive side has big areas, right? The areas here are big, 0.99. You want to look for the smaller areas. So we're trying to look for as close to 0.01 as possible. And that would be this guy right here, 0.0099. Okay, so it's between that and this one. But 0.0099 is a lot closer. It is a little bit more close to 0.01 than the one on the left. Okay, so 0.0099 is the winner here. So therefore my z critical is negative 2.33. So that's my z critical. All right, so now let's go ahead and write that down. So my z critical is negative 2.33. All right, so then we're gonna go ahead and draw the diagram. So this is the diagram. Left tail test, we went ahead and labeled our z critical, negative 2.33. And then we labeled our rejection region, the area here being 0.01 for the for this tail here, which is equivalent to my alpha. And that's my diagram. That's how it looks like. So let's look at one more example with critical values. So find the critical value and rejection region for a two-tailed test with alpha 0.10. So since it's a two-tailed test, we clearly have to find two critical values, one for the left, one for the right. And the critical values are always going to be one positive, one negative, but I'm still going to show you how to find both of them, okay? All right, so therefore we have a left area and a right area. So for the left area, you have, remember that the left area you need to do alpha divided by 2, because remember it's two tails, so you got to split the alpha into 2. So in this case, the alpha is 0.10 divided by 2. So it's the left area is going to be 0.05. And then for the right area, you got to do 1 minus that. Okay, so you got to do 1 minus the alpha over 2, which is the 1 minus 0.05, which is 0.95. Okay, so that gives you your, your alphas, your left area and right area. So let's go ahead and look both of those areas up. So let's look at 0.05 first. So let's see, 0.05 is a small area, so we got to go on the negative side. So 0.05 is around, again, it's between those two. So it's going to be either negative 1.64 or negative 1.65, depending on what you choose. So either one of those would be appropriate, okay? So I'm going to say either one of those, okay? I'm just going to choose one. I'm going to say negative 1.64, okay? So we have our z critical, negative 1.64. And then our right area, so our right area is when it's 0.95. And again, you're going to find that it's going to be the positive version of what we just found, but I still want to show you so that you can see. Again, it's between 0.9495 and 9505, which if you look is between 1.64 and 1.65. So positive. So therefore, if you find the left area and you get a negative value, just make it positive and that'll be your other critical value. Very simple. That's one quick way of doing it, just to save you some time. All right, so let's go ahead and let's go back to our diagram, or our left and right area. So this right area is z critical is 1.64. So basically it's negative 1.64 and positive 1.64. So let's show you this on the diagram. So you can see how it looks like for a two-tailed test. So those are my two rejection regions, negative 1.96, positive 1.96. Oh, wait, hold on. I might have messed up the numbers here. This is for a 10%, right? Yep, so that's incorrect. I apologize for that. This should say negative 1.64 and positive 1.64. All right, and that's for a 10%. Yep, okay, good. So that's the correct critical values. And then we got our rejection regions. And again, each of these tails is worth 0.025, right? So this is worth alpha over 2, and this is also worth alpha over 2. It's split amongst both tails. And it's not 0.025, it's 0.05. So I apologize for that confusion. So I want to correct myself real quick. Okay, because we said it was 10% divided by 2, which is 5% on each tail instead of 2.5. All right. All right, so now how do we use rejection regions in hypothesis tests? That's what we want to figure out next, okay? So first off, when you perform a hypothesis test, you always have to compute the test statistic. Just like we did earlier, you got to compute z-test. And in order to compute z-test, you got to use the formula for the z-test, okay? So I'm going to go ahead and reiterate that formula. In a little bit so that you have that formula with you. But once you calculate the test statistic, if it's in the rejection region, then you reject the null hypothesis. If the test stat is not in the rejection region, then you fail to reject the null hypothesis. And it's as simple as that. All right, so we're going to show you the three cases. So let's look at the left-tailed case. So if you have a left-tailed test, and let's say you found the critical value for your left-tailed test. Well then, if your z-test is in that rejection region, we said that we reject the null hypothesis. So the only way for the your test statistic to be in the region, in the rejection region, the only way for that to happen, to hit the red region, is if the z-test is less than z-critical or equal to it. So therefore, if the z-test is less than or equal to, we reject for a left-tailed test. That makes sense because you have to be in the red region to reject, right? Red means to reject. Now, for a right-tailed test, on the other hand, since it's on the right side, you have to be to the right on the right red region, right? The red region on the right. So therefore, when you calculate your z-test, if that is to the right of your critical value, or greater than or equal to, same thing, then you reject the null hypothesis. Simple as that. So if your z-critical was 1.5, and you calculated your z-test and you got 1.6, then you know you're in that rejection region, and therefore you reject. All right, now for a two-tailed test, it's the last case here. For a two-tailed test, if you're in the so you're going to have two criticals, right? A negative critical and a positive critical because of the two tails. If your z-test is either to the left of your negative critical or to your right of your positive critical, then you reject based on the image, right? That's shown here. So basically, if your z-test is less than or equal to your negative z-critical, or your z-test is greater than or equal to your positive critical, then you reject. Otherwise, if it's between the two, the negative and the positive z-critical, then you're going to fail to reject. All right. So those are your cases for using rejection regions for hypothesis tests. So then, what are the steps for the z-test critical value method? So let's go ahead and summarize that. Again, so your first step is to write your claim and hypothesis statements mathematically, which is the normal methodology that we use. Your second step is to identify your level of significance alpha. Again, that's normal. We did that in the other method. Your third step is to determine the test direction and sketch the standard distribution. We did that in the previous lesson. Step 4, though, is now you're going to compute, instead of computing the test value, you're going to compute the critical value, ZC, and then mark it on your distribution. So you got to do that first. Find your critical values using your alpha. And then you shade your rejection regions. And then you go ahead and compute your test statistic using the formula, make a decision, and then write a conclusion. Okay, so slightly different steps. In fact, there's one extra step. There's 8 steps here, 7 steps in the other one. All right, but essentially, they're pretty similar. All right, so let's look at an example. So Principal Vigu claims that the mean workday for his teachers is less than 7.75 hours. A random sample of 40 teachers is selected, and the mean workday is 7.5 hours with a standard deviation of 0.5 hours. Use an alpha equals 0.01 to test this claim. So first off, we need to identify, well, first off, normally we would say, can we actually do this? Can we actually do a z-test for a mean? And the answer will be yes, because the sample size is 40. So here we have our n, which is 40. We have our claim, which is saying that this is less than 7.75, right? So our claim is that the average is less than 7.75. So our mu is 7.75. So basically, this is our mu. It says from the sample, this is my x bar. That's your average, your mean workday. And then it says your standard deviation of 0.5 hours. So that's your S. Okay, that's your S in that example, your sample standard deviation. And then, of course, we got our alpha. All right. So yes, we can do this test because n is greater than or equal to 30. So yes, we can use it. All right. So first step is to do your hypothesis statements. So we know our claim. This claim belongs to the alternative hypothesis because that's a statement of inequality. Okay, so this is going to belong to H1 or HA, same thing. So we have mu less than 7.75. And then we're going to do the opposite of that. That will give us our null. So that's going to be greater than or equal to 7.75. It's key to have that equal to. The null hypothesis always has the equal sign. All right. So step 2 is to identify your alpha. Well, they tell us what that is. So 0.01, that step is done. Pretty easy. All right, your third step is to determine the direction of the test. That's determined by your alternative. So since it says less than, that means it's a left-tailed test. All right, less than means left-tailed test. Step 4, we want to determine the critical values. So this is where we have to find them. So let's go ahead and find our area. So we know that our area, let's do that over here. So we know that our area for a left-tailed test is alpha. And my alpha is 0.01. So let's go ahead and go to the z-chart, look up 0.01, and that will give us our z-critical. 0.0100, okay? As close to that as possible. And so that means we're going to go to the small areas. So we're going to go on the negative part of the chart, 0.01. The closest thing to that is that, 0.0099, which means the critical is negative 2.3, negative 2.33. There you go. So that's my critical value, negative 2.33. Done for that. Very, very simple. So we got negative 2.33. All right. So now we're going to go ahead and sketch the, we're going to do the curve. There's my curve right there. We're going to label our critical value there, negative 2.33. And shade our rejection region. So that's our rejection region right there. All right. Now let's go to the next step here. Step 5 is to shade. We did that. Now we got to calculate the z-test. So that's going to be x bar minus mu divided by sigma over square root of n. Now we don't have sigma, but we do have s. And remember that when n is greater than 30, we can substitute s for sigma. So therefore we can actually use s instead of sigma here, and that's perfectly fine for this test. So we got to do x bar. What's x bar? Well, they said in the problem that when they did the sample, they got 7.5 hours, and then the mu is 7.75. S is 0.5, and we have a sample of 40 teachers. Okay, so we have here 7.5 hours minus 7.75 for the mean over 0.5 for the standard deviation over square root of 40 teachers. So let's see what we get there. Do that on the phone here real quick. Okay. So we got negative 0.25 for the numerator. So we get about negative 3.16 to 2 decimal places. So that's my z test. All right, so we got that done. The step 7 is to make a decision. Okay, well, so let's go ahead and label that z-test over here. So that z-test is somewhere around here, negative 3.16. So that is clearly less than z critical. It's in that rejection region. Again, the red is the rejection region. We shaded it. So therefore, we reject the null hypothesis. So we reject H0. All right, what's our decision, or what's our conclusion? So remember, if we said we reject, that means that we have enough evidence. So there is enough evidence at the 1% level of significance to, now since the claim belonged to the alternative, we're going to say support, okay? Since the claim belonged to the alternative hypothesis, we have to use the word support. If the claim belonged to the HO or the null, then we say reject. So there's enough evidence at the 1% level of significance to support the claim that teachers work an average of less than 7.75 hours per day. All right, just kind of restate the claim in your own words, or use the claim that they give you. All right, so that's it, guys. So I hope you found this lesson useful, and again, like as usual, I'll see you in the next one.